It's time in our discussion to talk about electrical safety. Now, advanced warning, there are a couple images used in this video that might be disturbing to young children. So there's a couple pictures in here of some burn victims and results of some electrical burns. They are used with people's permission. They were published as a part of OSHA training, but just to make you aware. Okay, electrical hazards are everywhere. There's no way you're going to work in the construction industry and not come across potential electrical hazards. Okay, if we take a look at this picture, you can identify several electrical hazards and several issues that should be corrected. So, I mean, just to really quickly run down here, if you take a look at the breaker panel cover on the left, we have duct tape covering empty holes. We have an outlet cover that's not on and the screws are exposed. We have a crane that is probably touching power lines above it. And we have an outlet that has exposed wiring and the insulation cover is pulled back. All of these are hazards when it comes to electrical. So the whole idea is be safe, okay? Be safe reminds workers that burns, electrocutions, shock, arc flash, fire, and explosions are serious worker hazards from electrical power sources. So let's begin with some basics about electricity. Even though everyone viewing this is probably pretty knowledgeable about electrical, let's just do a quick review, okay? In electrical, we have electrons that flow with the path of current, okay? We also have resistance and voltage. Current is the movement of electrical charge. Resistance is the opposition to current flow. Voltage is a unit of electrical potential difference. The amp is a unit used to measure electrical current flow. Conductors are substances such as metals that have little resistance to electricity. Insulators are substances such as wood, rubber, glass, and bakelite that have high resistance to electricity. Grounding is a conductive connection to the earth which acts as a protective measure. Ohms are a way of measuring resistance. So if we take and compare an electrical circuit to water, water is the current, it's what's flowing. The pressure of the water is voltage. A valve could create resistance, okay, and it lowers pressures. And output, what's coming out of the end of the hose, is what does work. So we have two different types of circuits. We have a closed circuit and we have an open circuit. A closed circuit has a complete path for the electrons or the current to flow. An open circuit has an incomplete path. There might be a switch, a break in a wire, or something that does not let the current flow. Current is equivalent to voltage divided by resistance. Okay, the current is voltage divided by resistance. And this is known as Ohm's law. It takes 1 volt, okay, to push an amp through an ohm. Okay, because ohm is resistance, amp is the current flow, and voltage is the pressure affecting the current flow. So we have Ohm's law. Voltage equals current times resistance, or current equals voltage divided by resistance, or resistance equals voltage divided by current. The quickest way to do this is just put your finger or mark over whichever one you're looking for, and then just use the math. By the way, I stands for current. Okay, so we have an electrical circuit. Okay, and if you take a look at the picture on the bottom left, this is the example of a Romex conductor. We have a black wire most often, we have a white wire, and we have an uninsulated wire, that's our ground. Okay? So in a 220 amp, 240 volt circuit, okay, we will have two hots and a ground. The ground is always connected to the frame, to the ground rods outside, and a ground bar. Okay, ground is uninsulated most often. So factors that determine electrocution and shock include the amount of current, the path of the current, the duration of the shock, your body's resistance, the voltage, the frequency, and whether or not it's AC or DC current. Okay, so if you get shocked by 1 milliamp out of an ungrounded hand tool, okay, you may just feel a tingling. If you get shocked by 9 milliamps, you're going to feel a little bit more of a tingling and probably get burnt. 16 milliamps, you're going to get a really bad burn, but 70 to 100 milliamps, you may be lying on the floor dead. Again, a lot of this depends on what your own body can handle. Now, the estimated effects of AC currents, and this is a US standard, 60 hertz. Okay, our frequency is 60 hertz any place in the United States or Canada. Okay, 1 milliamp is barely perceptible. 16 milliamps is the maximum current an average man can grasp and let go. But what we mean by let go is if you get hit by an electrical shock, like grabbing onto a wire, you might not be able to release that wire. Your muscles will contract, and someone will have to knock you off that or turn off the current. Between 20 and 30 milliamps, you'll get paralysis of the respiratory muscles. In other words, you're not going to breathe. 100 milliamps is the ventricular fibrillation threshold. 2 amps, cardiac standstill and internal damage to your organs. 15, 20, 30 amp is our common US household breakers. In other words, think about this. You're going to get cardiac damage at 2 amps, but our breakers will not trip until you get to 15 to 20 amps or 30 amps in most US households. Okay, the path means that the harm is related to the path by which current passes through the body. Okay, if your path of the current goes from any place from your upper body into the ground or out of the ground, through your hands, through the center of your chest, those muscles, which include your heart and lungs, are going to be affected the greatest. So safe electrical work practices are listed here. Do not operate electrical equipment in wet conditions. Use insulated tools and equipment. Maintain tools in a safe condition. Properly use extension cords. Use non-conductive ladders. And you have to provide training. Unqualified personnel should be kept at a safe distance to not be exposed to energized parts. So again, here's the pictures here include several issues we see frequently in construction sites. We have hand tools with damaged cords. We have people dragging cords through a work site. And we have more extension cords with damaged parts. We need to be very careful with ladders around electricity. Okay, aluminum extension ladders anywhere in the vicinity of power lines are a problem. Don't do it. Okay, using aluminum ladders standing in standing water is a problem. Don't do it. Okay, don't use aluminum ladders any place near water or electricity, or even worse, both. Fiberglass ladders, even though they're sometimes heavier, they are the way to go. Also, be very careful of your height and clearance minimums, okay? Your ladder has to extend 3 feet over the edge that you're going to be climbing into. Be very cautious of your height, okay, and your overhang distance. But you have to be 3 feet above what you're going to climb onto. And always, when you're on a roof, tie that ladder to the roof. You don't want to get stuck up there without a ladder. We got to be relatively careful also of inadequate wiring. A hazard can exist when the conductor is too small to safely carry the current. For example, using a portable tool with an extension cord that has a wire too small for the tool. The tool will draw more current and overheating, possibly resulting in a fire without tripping the breaker. The breaker may not be the right size for the smaller extension cord. You also have overload hazards. This means there's too many devices plugged into a circuit. It can heat up wires and may cause a fire. If wire insulation melts, arcing can occur and cause a fire in the area where the overload exists, even inside a wall. Ground fault circuit interrupters monitor the flow between the hot and neutral wires. They will trip between 4 to 6 milliamps and 1/40th of a second. Okay, in other words, if there's a difference between the hot and neutral, which means some current is going someplace else, the GFCIs will trip in 1/40th of a second. They are designed to protect the worker by limiting the duration of an electrical shock. So again, the GFCI breakers takes a look at the hot conductor, measures the amperage. Then it looks at the return amperage from the grounded neutral. If you lose any difference, it means that there's current leaking someplace to ground. The whole object is that the breaker will trip. We need to have an assured equipment grounding program. Inspection is your primary protection. Best practice recommends documenting testing every 3 months. Okay, color coding in this documentation is very common. We have winter, spring, summer, and fall. When a power system is properly grounded, be aware the equipment can change from safe to hazardous due to extreme conditions and rough treatment. Don't assume, always check. We can have reverse polarity. Okay, that if for some reason the hot wire becomes reversed with the neutral, the tool could be hot with the switch turned off. Be very cautious of reverse polarity. Reverse polarity happens when the hot and neutral wire are reversed. Even though the switch is off, the circuit still could be hot. The switch could be turning off neutral, which does you no good because then all of a sudden neutral in the tool is hot. Some examples of OSHA electrical requirements with to temporary wire and lighting systems. The path to ground from circuits, equipment, and enclosures must be permanent and continuous. A broken ground pin increases the chance of being shocked or electrocuted and may create reverse polarity because it can be put in upside down. You may not use any tool or any extension cord that has the ground pin broken or removed. To protect a worker from shock, these tools must have a 3-wire cord plugged into a grounded receptacle, be double insulated, be powered by low voltage insulation transformer. Okay, you need to be very, very careful on grounding pins. Handheld power tools must be equipped with either a constant pressure switch, which shuts off power upon release. For example, what you find on a circular saw, chainsaw, grinder, handheld power drill, or it must have a full on-off switch, routers, planers, laminate trimmers, shears, jigsaw, nibblers, and scroll saws. Okay, has to have switches such as this. External extension cords cannot be used if the primary insulation is cut. If the insulation was also cut on conductors exposing bare wires, they could come in contact with someone or cause fire. Damage is often caused by repeated stretching or being run over. There's permissible uses of extension cords. Okay, you can use it for fixture wiring, portable lamps, tools, or appliances, or stationary equipment to facilitate interchange. Prohibited use of flexible cords substitute for fixed wiring, running through walls, ceilings, floors, or windows, concealed behind or attached to building structures. They cannot be permanent installations. Wiring must be protected in closed boxes. There's a potential of electrical shock from loose wire nuts or exposed conductors. Okay, electrical panel boxes. Live electrical panels must be completely covered with a hard cover. Employees can be exposed to live wires around the perimeter. You cannot use any cardboard as a protection. Junction boxes, pull boxes, and fittings must have approved covers. Unused openings in cabinet, boxes, and fittings must be closed. You cannot have any missing knockouts. This is a photo that shows violations of these two requirements. The knockouts on the side are missing, and there's no cover. And based on the wiring, you cannot get a cover on it. Electrical hazards may exist when there's tripped circuit breakers or blown fuses. If you have warm tools, wires, cords, connections, or junction boxes. A GFCI that shuts off a circuit. Worn or frayed insulation around a wire or connection. If you take a heat sensor, an infrared camera, and take a picture of a breaker panel, you can see hot spots. If there's hot spots, there's a potential electrical hazard. With handheld tools, insulated tools are the secondary protection and are not intended to be used in place of other PPE, which is personal protective equipment. When possible, always de-energize electrical power. Inspect tools prior to use for cracks, cuts, and other damages. If yellow insulation becomes visible through the outer orange layer, discontinue use immediately. Immediately remove any tool from service if it's not repairable or not repaired. If you end up throwing disconnects as a part of your work, there's a one-hand rule that applies. Stand out of the line of fire, turn your head away, take a deep breath, and hold it before you turn that disconnect on. Do not reach across the door. Okay, this is because it could have an arc flash or could have a major spark inside that and can sometimes actually blow apart the container. An electrical arc literally lasts less than a second. It has an extremely high radiant heat energy. It's explosive in nature, and it exerts great force. Electrical arcs can ignite or melt conventional work clothing. Lightning is an example of an arc flash. This picture shows what happens when someone replaced an electrical meter and had an arc flash incident. The meter blew up, it melted all the neighboring meters, and damaged the insides. This is the cause of the arc flash. And this was the picture of the victim's, the electrician's uniform. He was wearing the proper stuff, but still ended up in the hospital with major burns to his body. An electrical arc can have a temperature of 35,000 degrees. There's nothing you can wear that will 100% stand up to that. The copper will actually melt and turn the solid copper to a vapor, and that expands by 67,000 times. You'll have intense light. The air temperature will be over 500 degrees. You will have shrapnel that can move at greater than 740 miles per hour. You can have sound waves that are over 140 decibels. In other words, it can bust your eardrums. Pressure waves can include over 2,000 pounds per square foot. And you'll have molten metal at over 1,800 degrees Fahrenheit. That's an example of what happens if there's an electrical arc. The risk of arc flash depends on the number of times a worker performs a task involving exposed live equipment, the complexity of the task performed. Okay, do you need to use force? What's the available space, safety margins, reach, etc. The training, skills, and mental and physical agility, coordination with a helper, the tools used, and the condition of equipment. NFPA 70E is the requirements having to do with arc flash. It's the standard having to do with arc flash. So the requirements are that arc flash boundaries must be known and established. Safe approach distances must be established and maintained. Marking equipment relative to hazards. Electrically safe tools must be used. And you must wear personal protective equipment that contain arc thermal protection value appropriate for the job, and you must be trained. The minimum PPE requirement is hazard risk category 1. You must have long sleeve shirt and long pants or coveralls. You must have a hard hat on. You have to have safety glasses on. You have to have an arc rated face shield. You have to have hearing protection. Those are inserts, the little foam inserts on your ears. You have to have gloves. You have to have leather gloves over it and leather work boots. In other words, you cannot have any exposed skin when you're dealing in arc flash category 1. Labels must be required. Okay? They must contain the nominal system voltage, the arc flash boundary, and at least one of the following: available incident energy and corresponding working distance, or the arc flash category. You have to have the minimum arc rating of the clothing, and you have to have site-specific personal protective equipment. The best way to work on energized electrical equipment: don't. Shut it down and lock it out. You want to establish an electrically safe working condition. The lockout tagout procedures are simple. The company establishes the lockout tagout procedure, not OSHA. Key is kept with the worker who installs the lock. One lock, one key. You don't want to have a chance of anyone coming and removing your lock on a locked out system. We need to identify energy sources. We need to notify affected and other workers. You shut down the equipment, you isolate the energy source, you lock out and tag out. You release any stored energy, that would be capacitors. You verify that the energy is zero. You perform the required service, remove tools, notify all other workers. You release the machine from lockout tagout and re-energize. Again, tag, lock, one key. Overhead power lines are a major hazard in the construction industry. Overhead power lines most often are not insulated. Power line workers need to have special training and personal protective equipment. You never use metal ladders when working with or near electricity. You need to know where are the power lines. You need to understand their closeness to ladders and scaffoldings. Okay, this is an example of a piece of what's left of a piece of equipment that was damaged from overhead power lines. Okay, it blew the tires off the dump truck, blew the wheels apart, and the sad reality is that the worker in a bucket truck can actually be burnt to death and killed. Overhead power lines in the United States are not insulated. Any covering is generally a weather protection, not in insulation. Over 90% of the contacts occur on overhead distribution lines. Operators are normally safe if they stay on the equipment. People on the ground are over 8 times more likely to be killed. If you stay on the equipment, you become part of the energized piece of equipment. The people on the ground are the most likely to be damaged. If you touch a power line, electricity will attempt to travel through your body. When electricity travels through your body, it heats up and burns tissues internally. Electricity leaves the body violently, causing burns or even blowing an exit hole. You need to maintain safe working clearances from overhead lines. All equipment, that's ladders, scaffolds, cranes, trucks, forklifts, must maintain a minimum safety distance. You have to add 0.4 inches for every kilovolt. Minimum distance from overhead lines is 10 foot. Nothing can be closer than 10 foot. And if you have additional kilovolts over the standard, you have to add space. You have to ensure you always have adequate clearance. We have to install flag warnings at proper distances. If it is difficult for an operator to see the power line, you have to have a spotter. If you cannot maintain adequate clearances, you must have the power company insulate, move, or de-energize the line. You have to be very cautious around a piece of equipment that has touched an overhead line. The ground may actually be hot. Electricity dissipates with the resistance of the ground. As the potential drops, fields develop around the electrified machine. If you step across a line of unequal potential, you could be electrocuted. So if you take a look at the crane picture on the right that's touching the line, there's different fields based on the resistance of the ground, wet ground, dry ground, different soil types. As you cross these field boundaries, you could actually have a difference in potential from one leg to another. And even though you think you're safe because you're walking on ground, you can actually be stepping across and provide a path of current from one field to another. If contact with overhead power lines occur, you need to stay on the machine. You need to warn all others to stay away. You need to contact the power company immediately. Okay, you can attempt to move away, but you have to assure the line is not connected or trapped on the machine. If you have to jump out or bail out of a machine that has been connected to a line, jump. Do not touch the machine as you jump. Hop or shuffle out of the area. In other words, you want both legs to be in the same potential. Hopping or shuffling out of the area is the way to do that. Only qualified personnel should be permitted to work on electrical systems. De-energize electrical equipment before inspection. Make repairs using lockout or tagout procedures. Using electrical tools that are in good repair. Use good judgment when working on or near energized lines or equipment. Use appropriate protective equipment. Again, the NEC code book, okay, and the NFPA 70E is the arc fault. You have different classes of equipment. Conductive is 0 volts. Electrical is 20,000 volts. General is 2,200 volts max. To have incident-free work environment, it comes down to planning, training, inspection, oversight, lessons learned, and reevaluation.